Hello everyone, let's analyze. So today we're going to continue talking about the change of variables theorem and give a few examples. And we're also going to talk about when we can compute derivatives of functions inside of an integral. So just as a reminder, in our last lecture we defined what a change of variables is. This is also called a class C1 diffeomorphism, but for this lecture we'll stick with a change of variables. So G is 1-to-1 class C1 at least, and the derivative at every x is an invertible matrix, which is to say that the determinant of the derivative matrix is not 0. So the change of variables theorem, again, as given, is suppose A is open, bounded, and has volume, and G is a change of variables with the property that the determinant of the derivative and the determinant of the inverse of the derivative are bounded for all x in A. Well, if B is my change of variables of A, so it's G applied to A, if B has volume and F maps B to the reals is bounded and integrable, then so is the composition of F with G times the determinant or the absolute value of the determinant of the derivative of G. And furthermore, we get this equality of integrals. Typically, G of A is some shape for which it's not so straightforward to integrate, and A is often a rectangle or some other shape for which it is more straightforward to integrate. So let's see a few examples. Let A be the region bounded by the four curves below. Let's compute the integral over A of x squared times y cubed. So, well, what are those curves? Well, the two straight lines are y equals x and y equals 4x. And the two curves we see are all points x and y whose product is 1, and all points x and y whose product is 2. So then A is the region bounded by the intersection of these four curves. Of course, we could set each pair of curves equal to each other and solve for those corner points. And in fact, we can show that A is just a warping of a rectangle with width 1 to the square root of 2 and the vertical edge going from 1 to 2. So in fact, if we were to apply the change of variables given here, G of uv is u divided by b comma uv, and apply that to this rectangle, I would fall right on top of this red, right? So this black dashed is this change of variables applied to this boundary, and of course the interior of R is mapped to the interior of A. Right? Of course, we can show that the determinant of G is invertible for all u and v inside of here, but of course the inverse function theorem would only guarantee that G is locally 1-to-1. We would need G to be 1-to-1 on the entire set of R, and one could show that, right? We'll omit that, but you could show that G is invertible or 1-to-1 on the entire set R, and not just locally everywhere. So A is the mapping by G of a rectangle R, and again one can confirm that G satisfies the conditions of a change of variables. So in order to utilize our change of variables theorem, we'll need the derivative. The derivative is the matrix whose first row is the gradient of u divided by v, and the second row is the gradient of u times v, so which we have here. And the determinant of the derivative g is given by 1 over v times u minus, so plus uv over v squared, which is just double u divided by v, which, so long as u and v is inside of my rectangle R, is necessarily positive. So we can drop our absolute value sign, and we have what we need to apply the change of variables theorem. So the integral over a of x squared times y cubed is the integral over the rectangle R of g1 of uv squared times g2 of uv cubed times the absolute value of the determinant of the derivative du dv. The determinant of the derivative is positive in my rectangle R. G1 is u over v, so I square that. G2 is u times v, I cube that. And the determinant of the derivative is 2u over v. So that's u squared times u cubed times 2u. That's 2u to the sixth, and I have v cubed divided by v squared and divided by v. So my v's cancel. So the derivative of 2u to the sixth power, u to the seventh, from the square root of 2 to 1. I get 16 times the square root of 2 minus 2 over 7. And if I integrate that from 1 to 2, of course now my integrand is independent of v, so I'm just computing the area of a rectangle with width 1, so I just get my integrand. Now let's play with an asteroid. So let's compute the area of an asteroid, aka a tetracuspid, aka a four-cusp hypocycloid. By the way, why is it called a hypocycloid? Well, a cycloid is a shape by essentially following a point on a circle as you roll it along surfaces. So for example, if you were to take a Firestone tire and roll it along the floor and follow the F in space as you roll the tire, you would get a cycloid. Well, you could also roll that same tire on other surfaces, not just a flat ground. If you were to roll it on the inside of a bigger circle, you would get what's called a hypocycloid, and that's what we have here. So the boundary of the hypocycloid can be parameterized by theta, and the boundary for some positive value r is just r cosine cubed theta, r sine cubed theta, where theta is in the interval 0 to 2 pi. Right, so the area enclosed by the curve can be described by g of r theta, where we just scale a of theta by r. Right, so long as r goes from 0 to capital R, we get the boundary and the inside. So now that we have our asteroid described as a warping of a rectangle, and of course we could confirm that G does in fact satisfy the conditions of a change of variables, so we can use the change of variables formula. Right? The area of the asteroid is just the integral of 1 over the domain of the asteroid equals the integral over the rectangle E of the absolute value of the determinant of the derivative of the change of variables G. So, well, we're going to need that derivative. Right? So the derivative of our change of variables, and that would be cosine cubed theta in the first entry, negative 3r cosine squared sine in the second entry of the first row, sine cubed in the second entry of the first column, and that bottom right corner is 3r sine squared theta cosine theta, which when you take the determinant is 3r cosine to the fourth power times sine squared plus 3r cosine squared times sine to the fourth. And well, we can start to cancel. There's a cosine squared and sine squared in each term. We know when we sum that, we get 1. Here's where we can use the double angle formulas for sines and cosine to simplify our work. And we'll let's use that double angle formula just one more time. All right, so here we got a little help from our friends. As I mentioned, the double angle formula of cosine given in red and the double angle formula of sine given in light blue. So now we can compute the area of the asteroid. It's the integral over a rectangle of our function of r and theta. Because we're integrating over a rectangle, right, it's just nested real integrals, right, over an interval in the real line, which, right, are just nested calculus 1 style integrals, so we can compute them straight away to get a number. 3 pi r squared over 8 is the area of our asteroid, aka tetracuspid, aka quad cusp hypo cycloid, if you're fancy. Okay, let's look at another example. All right, so let's consider the closed sphere in 3 dimensions, and let's compute the integral of the norm squared of a vector x, of course in 3 dimensions. So the sphere can be described as the change of variables from a 3-dimensional rectangle, otherwise known as a rectangular prism, using the following change of variables. Now, you've probably seen spherical change of variables before, and there are several variations, but just in case you're wondering where that change of variables came from, let's take a look at how they're computed. So here we have a sphere in 3 dimensions. We have the 3 axis coordinates. So let's begin at 1, 0, 0, or at E1. And well, we can rotate by theta along the equator. So along the equator, I just have a circle parameterized by theta, cosine theta, sine theta. The third coordinate is 0 because I'm still on the equator. And I can go all the way around. In other words, theta would be in the interval 0 to 2 pi. Now, I can travel northward or southward along the surface towards the poles by rotating by phi. So we see that the x1 and x2 coordinates would have to get scaled by the cosine of phi, right? That would be this magenta part here. And then of course the z coordinate would just be the sine of phi, which is exactly what we have here. And that'll get us anywhere along the surface. Right, of course, as we rotate up or down by phi, we don't go past the poles, because if we were to go past the poles, then we could have just traveled further along the equator and then gone northward or southward there. And by the way, this also matches the convention of latitude and longitude, even though they use degrees, and, well, the Earth isn't exactly a sphere, it's just slightly ellipsoid. Enough to make a difference if you're using GPS, for example, to get to a restaurant, if your GPS doesn't take into account that the Earth is a ellipsoid and not a sphere, of course, you might end up in a cow patty somewhere. Now, with GPS systems as they are in Texas, with so many rural roads, you might end up in a cow patty anyway. Now, of course, to get inside, we can always scale that radius by some number between 0 and big R and get back and forth. So r, right, would be the distance from the origin. So that's where that comes from. To utilize our change of variables approach, we would need to compute the derivative of this spherical change of variables, which is given here. I would encourage you to double check that, pause and work through this computation. We can take the determinant, right? That would give me r squared times cosine of phi, and again I would encourage you to double check that work and to go through those computations on your own. Now note that the integrand, right, composed with the change of variables is just the radial length r squared, right? Because the integrand is the norm of x squared, and the norm of x is, well, just the distance from 0, right? We're using the 2 norm here. So the norm of x in spherical change of variables is just r, and the norm of x squared is r squared. So the integral over the sphere of the norm squared is equal to the integral over my rectangle of r squared times, sorry, I'm missing here a r squared cosine phi. That should be right there. Now I have it here, that's why this r became r to the 4th power. And here I expanded my rectangle into my nested calculus 1 style integrals to get 4 pi r to the 5th over 5. So now we're going to discuss combining differentiation and integration, or when we can compute the derivative of an integral function. So suppose f is defined on a rectangle in R2, and it's real valued and continuous. And the derivative with respect to y is defined and can also be extended to be a continuous function on the rectangle. Right, for each given x, we have this continuous function with respect to y of the partial derivative of f with respect to y. So if big F of y is defined to be the integral from a to b in the x direction of f, then big F is differentiable, and the derivative of f is the integral of the partial derivative of little f. Okay, so we'll go through the proof fairly quickly because I want to play with it, to be honest. But let's go through it. So I need to show that this difference, right? I need to show that this difference converges to 0 as h converges to 0. Of course, here I'm using the definition of what big F is, which is defined here, so I just replaced it here. And I can simplify this integrand by using the mean value theorem, right? The mean value theorem says there is some number c, right? For each x, there is a c on the interval from y to y plus h for which this is equal. Therefore, replacing this integrand with this partial derivative gives us exactly this here. And then we could use essentially the extension of the triangle inequality for integrals to get an inequality here. Now, since the derivative of f with respect to y is continuous on my rectangle, for each x I have a continuous function of y, then the derivative of f on this rectangle is uniformly continuous, right? Because I have a closed rectangle. So it was continuous, it's on a closed domain, so it's uniformly continuous. So for every epsilon, there is a delta such that if x naught and y naught and x and y are inside of my rectangle, so long as the difference of those 2 points is less than my new delta, my delta prime, then my difference of the partial derivative, which is continuous, is less than whatever I want. And what I want is epsilon divided by b minus a. The reason I want that is because, well, if you remember where we left off on the previous slide, down here at the bottom, this difference is less than epsilon divided by b minus a, which when I integrate from a to b is just epsilon. And because epsilon is arbitrary, what I wanted to go to 0, this here, what I wanted to go to 0 does in fact go to 0. And I've proven my result. Okay, now I really want to play with it, but before I can, we need to extend the idea to infinity, and we can. It's a very similar theorem, except that now b has become infinite. So suppose f is defined on the infinite half strip, a to infinity by c to d. It's real valued and continuous. And the partial derivative for each x in my half strip is continuous on the half strip. Furthermore, assume that the integral from a to infinity of f with respect to x converges for all y, and that the integral from a to infinity of the partial derivative of f converges uniformly for all y, right? Specifically converges uniformly to a function of x for all y. Then if big F is defined as before, the integral of little f with respect to x, then the derivative of big F of y is equal to the integral with respect to x of the partial derivative of little f. And again, the proof would be very similar to what we just did because this theorem is essentially the same as the previous, except that b has become infinite, which is why we added this condition of the integral of the partial derivative being uniformly convergent. Okay, so let's work out an example. So let's find the integral from 0 to infinity of x to the n times e to the negative ax by repetitively differentiating the integral from 0 to infinity of e to the negative ax. Now, of course, we could get right to repetitively differentiating, but of course, we should justify why we can actually take such a derivative, and that is a mathematically valid step. So let's consider our half strip of 0 to infinity by epsilon to r. And f, right, is this integrand here. F of x comma a is the integral, is e to the negative ax. So I have a function of a and x. Right? This is an integral with respect to x, so I want to take a derivative with respect to a in order to get this, but I have to justify that action. Well, f is clearly continuous on my half strip, and the derivative of f with respect to a is negative x times e to the negative ax, right? Negative x times little f, right? So the product of two continuous functions, so it exists and is continuous on my half strip. Furthermore, the integral of f is 1 over a, so the integral exists, right? Because it's an infinite integral, right, we would say actually that the integral converges because, of course, anytime you have an infinity as a integral limit, then you're really taking a limit, so you're talking about convergence. Similarly, the integral of the derivative with respect to a also converges. But remember, that's not enough, right? It's not enough that I converge to a function of a. I need to converge to a function of a uniformly, which is to say that the convergence, the rate of convergence, doesn't depend on a. That is, I converge at a uniform rate for all a in my half strip, no matter where a is, right? So I have to show that the convergence is independent of a. So, in other words, I need to show that this difference can be made arbitrarily small so long as b is big enough, but the big enough cannot depend on a at all. And I can do that by, well, taking my integral. I would get this, right? I get a plus 1 over a squared minus 1 over a squared. So this cancels. So I have this here, but remember, I need to get rid of my a. Okay, I can factor out an a, but I need to show that this is bounded by something independent of a. Well, in fact, I can do that because a is between delta and r. A is bounded by r above and by delta below. Therefore, I can bound this using r here and delta here, and then also delta there, right? Because A is coming from a closed interval and is bounded above and below, right? I can do that. So now I have a bound that is completely independent of A, and it goes to 0 as B goes to infinity. So the integral converges uniformly to -1 over a squared, right? Because our theorem says that it's not enough for the integral of the partial derivative to converge. It specifically has to converge uniformly. But now I have satisfied my conditions of the theorem. I'm now authorized to take derivatives. So let's do so. The derivative of f, right, I'm sorry, that's a typo. This right here should say a. F of a equals. So my apologies. That's f of a. So my derivative with respect to a is equal to the integral of the partial derivative with respect to a. I can pass my derivative underneath the integral because I've satisfied the conditions of the theorem. And well, that's equal to negative the integral from 0 to infinity of x, e to the negative ax. But we also know that f of a is 1 over a. And the derivative of 1 over a is just -1 over a squared. So in fact, this integral equals -1 over a squared, which is what I have here. They both have a negative, so I can drop it, which is what I have here. And, well, using similar arguments, I can repeat that process. I can keep taking a derivative, right? Now, I've justified taking a derivative of this. To justify taking a derivative of this, I would need to show for this all the things I showed for this, but I could using, right, similar types of arguments. So I can continue taking derivatives. If I continue taking derivatives of e to the negative ax, I'd get -1 to the nth power, because I'm going to be flipping signs as this comes down, right, times x to the n. Of course, we also know that f of a is 1 over a, and the nth derivative of 1 over a is -1 to the n times n factorial over a to the n plus 1. So in fact, this term here equals this fraction here. Now, both have a -1 to the n, so I can get rid of that to obtain that the integral that we wanted to compute is equal to n factorial divided by a to the n plus 1. So we've accomplished the task set out to us by the example. So now, where did this example come from? Well, if a is equal to 1, we've shown that the integral from 0 to infinity of x to the n times e to the negative x dx is equal to n factorial. In fact, the gamma function developed by Daniel Bernoulli, defined by gamma of z plus 1, equals the integral from 0 to infinity of x to the z e to the negative x dx, is in fact a smooth extension of the factorial function to the reals. Even more, it's actually an analytic extension of the factorial function to the complex plane, except for negative integers. So, the gamma function evaluated at n plus 1 is n factorial. So we actually have a smooth function that extends the factorial function to, well, any real value. Well, that was fun. That's all for today.